Hello everyone, welcome to another CNCM video. Today we're going to go over an interesting solution to an AMC problem. And the AMC problem we're going to talk about is from the 2021 AMCs. It is the 2021 AMC 10A number 23 and 12A number 23. So the problem reads, Frida the Frog begins a sequence of hops on a 3x3 grid of squares, moving one square on each hop and choosing at random the direction of each hop, up, down, left, or right. She does not hop diagonally. When the direction of a hop would take Frida off the grid, she wraps around and jumps to the opposite edge. For example, if Frida begins in the center square and makes two hops up, the first hop would place her in the top row middle square, and the second hop would cause Frida to jump to the opposite edge, landing in the bottom row middle square. Suppose Frida starts in the center square and makes at most four hops at random and stops hopping if she lands on a corner square. What is the probability that she reaches a corner square on one of the four hops? So, before we get started, let's look at what we want. And so we want the probability that she reaches a corner square on one of the four hops. This is the same thing as saying that that this probability, we'll call it P of A, I guess. Make it capital A. And let's call probability B the probability of, well, not reaching a corner square at all on any of the four hops. And this is, if you subtract this from 1, this is equal to probability of A by complementary counting. Why is that so? Well, if you don't reach a corner square on any one of the four hops, you're not going to stop at all. And that means basically if you haven't stopped and you land on a non-corner square on the fourth hop, that means that the other event, that any other event would just be you either land on a corner square on the fourth hop or you, well, stopped your hop sequence earlier because you reached a corner square. So if we can find this probability right here, then we can do the problem. Now, it's hard to find this probability specifically, but there is a recursive solution. And if you're to draw a grid, and we can use this to represent the problem, it's a type of recursive grid. We can denote this as the number of ways to reach each square. When we make 0 hops, of course, there's one way to reach the center square, 0 ways to reach every other single square. But that changes when we go to 1 hop. When we go to 1 hop, I'll draw this over here. When we go to 1 hop, well, let's think about it. From the center square, can we reach the center square from the 0 hops? No, because obviously the frog doesn't have the option to stay, so there's no way to go here. But are there ways to go to any other square? Well, we can't go here to any of these corner squares because they're diagonal of the first center square in 1 hop. But we can go to these squares on the edges. So we can either go here, 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 or here. And that represents the 4 ways that Frida can go in, well, the first hop. And now if we go do the second one, then you can see, well, how many ways are there to reach the center square? Well, we can reach the center square from either this square, this square, this square, or this square. And there's a 1 in each of these, so if we sum those, that's 4. How many ways are there to reach this square in particular? And that'll be symmetric across the other 4 squares. Well, you can only reach it, actually, the only way to reach that square is if you go down from here. And that'll wrap you around to here, as the problem says. So there's only one way to go there, so that's going to apply here. How many ways are there to get to a corner square? Well, we can get there through here if we go down, but this is 0, so there's no ways from there. We can also just move alternately. We can just move from this square over, or this square over. We can also move from this square over. Those are the 4 ways to get to this square, but as you can see, these 2 have 0s, so we don't have to care about them. But these 2 have 1, so there's one way to get to this square, one way to get to this square in total. So there's 2 ways to get to the corner square, and everything is going to be symmetric. And if you want to do a sanity check, this adds up to, I believe, just make sure, it adds up to 16. and 4 squared, which is the number of sequences you could get by hopping, is 16. If you were to continue this to 3 hops, 4 hops, this is what you would get. But we can't use this solely to solve the problem. We have to do a little twist on it. We want to find probability B. And the reason why we're not finding probability A directly on these types of grids is because the frog stops hopping if the frog reaches a corner square, and that's a bit complicated to account for in a recursive solution. So we're trying to find probability B because we don't have to account for stopping. We can just find the probability after 4 hops that she doesn't reach a corner square. Now, how would we do that? Well, we can still use these grids. So let's say we were here. We're at 0 hops. Of course, there's only one way to even do anything here, and that is just staying because we haven't made a hop yet. And we're trying to find probability B. If you remember, it's the probability of not reaching a center square. Not reaching a corner square, I'm sorry, not reaching a corner. We can write that. And so how do we account for that? Well, we just don't consider the corner squares at all. We'll keep them at 0 because if by disregarding them, that means we're not accounting for the frog jumping on the corner square, which is good, that's something we want. So let's go to the first top. If we go to the first top, we can see that, well, there's no way really to reach the corner square. We're not focused on the corner square. In fact, we're only focused on these 5 central squares, if you can see here. We're only focused on those 5 central squares. We're not really focused on the 4 corners, but I'm here just for the simplicity of making the grid. So as we said earlier, if we go back, this is the grid after 1 hop. It's the same thing because we're not reaching any corners. And there are 4 ways to do that. So there you go. So what about 2 hops now? Now things are going to change. We said that we don't want to land on a corner square, so we're not going to consider the corner squares at all. Just pretend they don't exist. How many ways are there to get to the center square? Well, similarly, we can get there from any one of these like middle squares on each of the edges. And so there's ones in each of them, so they sum up to 4. So there's 4 ways to get there. How many ways are there to get to this thing? Well, we can go down and travel and wrap up because that's what happens if you go off the board. So there's one way to get here. Since we can't, there's no total in here, so we can't just go up because there's 0 ways. So there's one way to do that. And by symmetry, there's going to be one way to do that, one way to do that, one way to do that. So what about 3 hops? I'll put zeros here for simplicity, just for the purpose of showing that. Well, 3 hops, how many ways are there to get to the center square? Well, we can get to the center square from each of these edges once again, and that sums up to 4 again. So there's still 4 ways to get to the center square. How many ways are there to get to this square in particular, though? Well, we can travel up from here, which we can do 4 ways, because we have to sum the 4, and we can wrap around from the bottom. And that's 4 plus 1, 5 ways to get there. And so by symmetry, once again, there's 5 ways to get there. Remember, we're disregarding the corners here, because if she doesn't land on the corners, why would we want to account for getting to this square from a corner? So we're just counting the complement. We're not doing anything complicated, just counting the complement. We're not accounting for the corner squares. So what happens on the final step? This is the last step we have to account for. Well, how many ways are there to get to the center square again? Well, it's just the sum of these 4 edge squares, as we said earlier, so that's 20. How many ways are there to get to this top square? Well, you can go up or you can wrap around. So that's 4 plus 5, 9 ways. And by symmetry, it's going to apply here and here and here. So on this grid, we're disregarding the corners because we don't want to land on a corner. And in each of these squares is the number of ways to get to that grid at the end of 4 hops. So after some sequence of 4 hops, each one is accounted. Each one that lands on a square that's not a corner is accounted here. So we just sum this up. That's 20 plus 4 times 9 is equal to 56. 56 ways to get to a non-corner square after 4 hops. And notwithstanding the corners in any one of those hops, because we've never accounted for the corners in any one of these grids. So, and we know that we've completed 4 hops and Frida can travel 4 directions in each hop, so it's, the number of total ways is 4 to the 4th is equal to 256. So probability B is 256. We want probability A, which is the complement 1 minus PB, uh, and that is equal to, well, if you subtract by 1, that's going to give you 200 over 256. Subtract from 1. Now we just got to simplify this. This is our probability of landing on a corner on at least landing on a corner on one of the hops, and that is going to be, if you do some simplification here, the number of power, this is power 2, is, in particular this is 2 to the 8th. The greatest power 2 that goes in 200 is 8, which is 2 cubed, so if we do some cancellation, it's going to yield 25, it's going to yield 2 to the 5th, which is going to be equal to 25 over 32. And so that is our final answer. Going back, it is indeed an answer choice. It is answer choice D. And so here is an interesting solution to this problem. I just thought it was an interesting solution using these recursive grids. Nothing really, any states. It's a simple solution. It wouldn't take you long to execute in context. Just a little bit of logic and some simple grids got us to solve this number 23. So that's just an interesting take on the recursive grid method of solving some of these counting problems on the AMCs and AMEs. And that's all I have for you today. Thank you for watching.